All right, hello everyone. My name is Stephen Yagmore, and welcome to the Mass and Energy Balances Crash Course series. Today we're going to start with our first real lecture, which is going to be simply prerequisites for mass and energy balances. In my overview lecture, I talked a little bit about some of the topics we'll be covering and some classes you should take. But in this one, I'm just going to cover a little more in depth about some of the specific topics, the prerequisites that's needed for mass and energy balances. Just as an overview really quick, I go through a few examples in this lecture for some of these prerequisites. It's not going to be super in-depth. I'm going to list off the topics here in a second, but it's really important to have a good understanding of all these topics I'm going to discuss before going through with the lectures of mass and energy balances. So looking at the topics here, first we have unit conversions and knowing how to use unit conversions. Then we have density and specific gravity, understanding the definitions and the equations that correspond with them, understanding flow rates and specific values, knowing how to use stoichiometry as well as concentration definitions, understanding mass and mole fractions and how to convert between the two, and finally understanding basic calculus such as differentiation and integration. I'm not going to go through super in depth each of these topics. We're going to briefly cover them, go through really quick examples, very basic examples for each of them. If any of these topics, as you go through, are something that you struggle with a bit more and something that you need to maybe refresh, I highly recommend finding some other resources, going back to any class notes or other videos that you may have, and getting a better understanding of these topics. But with that being said, we're going to go ahead and give a brief overview of each of these topics here. So the first one we're going to take a look at are, well, unit conversions. So the first thing that's really important with unit conversions is understanding what they are. In chemical engineering specifically, there are so many different quantities that we need to measure out. As you can see here, each of these rows in this table that we have here are honestly really important for chemical engineering. Mass, length, volume, density, force, pressure, energy, power. Each of those will come up at some point in chemical engineering or in physics in general. So it's really important to understand how we measure these. We measure them using these units. And a lot of times when solving problems, it's really important to know how to convert the units between each other. Because when you're doing arithmetic, when you're adding two different masses together, when you're subtracting lengths between each other, you need to make sure you're doing everything in the same units. And when you're given two different values with different units, you need to know how to convert from one unit to the other. It's really important to find conversion factors. There's so many of these types of tables online that you can look up. I think this is a really good table. For example, it shows so many different quantities and shows you 1 kilogram is equal to 2.20462 pound mass. It shows that 1 meter cube is equal to 264.17 gallons. This one's really nice. You just decide what quantity you're dealing with, volume, density, force, etc. You go to that row and you see what unit conversions are there. Another really good resource is also Google. Going and just Googling, how do I convert from this value to this value? And almost every single time, a nice little calculator will pop up for you, and you can just type in the number, and it'll honestly automatically just give you the value. It's also really important to know how to use unit conversions, though. Another big aspect of units, especially with the metric system, are prefixes. With the metric system, the imperial system does not do this as much, but the metric system, which is really heavily used in engineering and science, the science community in general, these prefixes allow us to gauge an understanding of different values of mass, of volume, and of length. So for example, we have 1 meter, which is really simple as a base unit of 1. And from there, we can decide how much or how little of a meter we have based on these prefixes. If you have multiple meters, in that case, if you want to shrink down the number, you use kilo in front of it, which multiplies it by 1,000. If you want a much shorter distance, you can use centimeter, or millimeter. They're really important, and they each have a different power of 10 associated with it. The power of 10 is really nice, really important, makes for really quick and easy conversions. It's really important to understand these, especially when you get down to the smaller ones. Those ones are used a lot more than lead on, the micro, nano, pico. It's important to understand those two and differentiate and understand how we can convert between one another. So really quick, we're going to just quickly go through a unit conversion example. Let's go ahead and take 5.00 BTU per minute squared. Let's convert that to joules per second squared. So the most important thing to go about unit conversions, basically just starting with one unit, one of the quantities, converting that one to the other one that's necessary, going and doing that one, and then starting with the second one. So it's really just a matter of, picking your order, picking which unit do I convert from to and from first. So let's go ahead and start with the energy values, BTU and joule. So BTU, for those that don't know, that's the British thermal unit, I believe. And it's really common for imperial units. Metric system uses joules, however, that's the SI unit for it. So what we can do is we can look on a table, we can go on Google for purposes of this lecture. I'll look on the table here and say, okay, I need to know the unit conversion between joules and BTU. I know those are energy. So I go to the energy row, and I go ahead and I pinpoint the values I need. I can see on this table, 1 joule is going to be equal to 9.486 times 10 to the negative fourth BTU. So those are the values I'm going to use in this case. So when going about our unit conversion, it's always straightforward. We go ahead and we start with our value. Now, a lot of different people understand that we need to multiply and divide to make sure that we get our unit conversions going correctly. Some people use the train track method. I'm just going to go ahead and multiply straight out, just show the multiplication. So we start with BTU per minute squared, and then we're going to multiply that by the conversion factor we found, 1 joule over divided by 9.486 times 10 to the negative fourth BTU. We make sure to do it in that order with joules on top because we want the BTU to cancel out. So you can see with the top and on the left side it's on the top and the right side it's on the bottom, they go ahead and cancel out. We're left with just joules. So now we need to go ahead and convert the minute squared to second squared. So as we know, there are 60 seconds in 1 minute. So we're going to go ahead and use that conversion. The minute squared will be on top because minute squared is on the bottom on our first term. And then we have 60 seconds, but we need to make sure to square the 60 in 60 seconds as well, because we're dealing with seconds squared and minutes squared. Whenever value is squared, you can't just use the normal conversion. You need to take that conversion to whatever power is being used. In this case, it's not just going to be 60 seconds. It's going to be 3,600, 60 squared, 3,600 seconds squared. That's going to be really important when doing this. And from that, our minutes squared will cancel out, giving us approximately 1.46 joules per second squared. Every single unit conversion problem is essentially some form of this. Fairly straightforward overall. Make sure to freshen up because it's really important to know for mass and energy balances and in almost every single science course in general. Temperature conversions are also a bit important. There's 3 really most commonly used forms of temperature. You got Fahrenheit, Celsius, and Kelvin. It's important to convert between the 3 of them. If you have Fahrenheit to start out with, degrees F, and you want to convert to degrees C, which is Celsius, you can go ahead and use this equation. You take your temperature in Fahrenheit, subtract 32 from it, then multiply by 5/9, and that gives you Celsius. If you want to go the other way around, you start with Celsius, take your temperature and immediately multiply by 9/5, then add 32 to it. Notice how there's no parentheses here, and there's parentheses in the previous one. That gives you the order of operations to follow. If you do that, that gives you degrees Fahrenheit. And then finally, the most important one, in my opinion, is going to be converting Celsius to Kelvin. It's the most straightforward out of all of them, thankfully. It's going to be the one you end up using the most. You do is you take degrees Celsius and you just add 273.15. And that gives you degrees Kelvin. Kelvin is very commonly used, especially as we delve into the energy balances of things. It's going to be really important to use Kelvin in some instances over Celsius. So making sure to know when and how to do this conversion is going to be really, really important. One of the most common slip-ups for chemical engineering. Now that we covered unit conversions, let's go ahead and talk about density and specific gravity. The definition of density is pretty straightforward, hopefully something covered in high school a fair amount. It's simply mass over volume, just mass per volume. That's all density is. You have a substance, it's going to be the mass of that substance over its volume. It's an intrinsic property, meaning as long as you're at a common temperature and pressure, you can assume that density is going to be the same no matter how much of that substance you've got. If you got 500 kilograms of the substance versus a few grams of the substance, the density is going to be the same because it's mass per volume. Going to be represented by this equation here. Density is almost always represented as rho, which is a Greek letter. You can see here density is rho. The mass is represented by m, and volume is generally represented by a v. Those are the most common variables that are used in this equation here. Going through a quick example of density. What is the density of a solution that has a mass of 3.0 grams and a volume of 5.0 centimeters cubed? We're just going to go ahead and use the equation that we have back on this slide here. Fairly straightforward. Density is mass over volume. So you can see we're given the mass, 3.0 grams. We're given the volume, 5.0 centimeters cubed. It's a simple division at that point. Density is going to be 3.0 divided by 5.0. When you do that division, you get about 0.60 grams per centimeters cubed. Fairly straightforward example of density. Now, what's a little bit more confusing, but not all too confusing when you get down to it, is the idea of specific gravity. Specific gravity is the unitless ratio of the density of the analyzed substance to the density of some reference substance, usually water. So what do we mean by analyzed substance and reference substance? Let's take a look at the equation first to get a grasp of things. So we have specific gravity, Sg. It's going to be defined as rho, which is the density of our analyzed substance, over rho of, and I just put rho of H2O, which is our reference substance. So it depends on what you're taking the specific gravity of. If you have the specific gravity of oil, then rho, that density value, is going to be the density of the oil. If you have the specific gravity of blood, then the rho is going to be the density of blood. The rho and the specific gravity are related. It's whatever material, whatever substance you're looking at. The rho H2O, almost every single time that reference substance, that bottom term, is going to be water, unless in the text or in a problem statement you're specified otherwise. Sometimes they may say, okay, the reference substance is going to be some other liquid, some other compound. That is okay. Just make sure to use that density instead of the density of water. So what values do we have for the density of water? Well, for this reference substance, we're assuming it's water at standard temperature and pressure. So at standard temperature, which is going to be 25 degrees Celsius, we're going to have the following different values, different units for the density of water. We have 1.0 grams per centimeter cubed, 1.0 kilogram per liter, 1,000 kilograms per meter cube, and 62.4 pound mass per foot cube. Now, how do we know which one of these we want to use at any given time? That's going to be really dependent on the problem that you have at hand and what other values that you have. The most important thing is you want the density of your substance, the top row, and the density of water, that rho H2O, you want those to have the same units, because specific gravity needs to be a unitless value. It's a ratio in this case. So you need to make sure those units match up so that they cancel out. Let's go ahead and look at a problem to kind of understand what I mean by this. So what is the mass of a solution with a specific gravity of 1.09 and a volume of 2.4 liters? So we know a couple things here. We're solving for mass in this case. We want to know the mass of the solution, but we do have a volume, 2.4 liters. And going back to our previous slide, we know that mass and volume can be related by the density. Density is mass over volume. So we want to find the density. We're not directly given the density, but we are given a specific gravity of our solution here. So let's look at the specific gravity equation. Sg is equal to rho over rho H2O. Can go ahead and plug in the value for specific gravity we have. It's 1.09. Now the question is, to solve for our density, rho, we need to pick a value for rho H2O. And the question is, which of these values are we going to pick? Well, look at the problem statement. It says that we have a volume of 2.4 liters. It's going to make the most sense for us later down the road if we pick a density that has liters in the unit somewhere. The only one that we have with liters in the units is going to be this value here, 1.0 kilogram per liter. It's going to make the most sense to use this for our density, because when we solve for mass later, it's going to make things a lot easier for us because we have similar units. So now if we go back and plug in the values we have, specific gravity is 1.09. That's going to equal rho over rho of water, which is 1.0 kilograms per liter. Carry out the multiplication, you get rho, the density of our solution, is going to be 1.09 kilograms per liter. Now that we have the density, we can go ahead and solve for the mass. Go back to the equation here. Rho is equal to mass over volume. From there, we can plug in the values we know. Density is 1.09 kilograms per liter, and the volume is 2.4 liters, leaving us one unknown variable, mass. We can go ahead and solve. We get mass is equal to 2.62 kilograms. Fairly straightforward problem to go ahead. Most important part, knowing what units for your density to pick and knowing how to use these two equations side by side. Now that we talked about density and specific gravity, let's go ahead and take a look at flow rates and specific values. Flow rates are defined as the amount of substance that flows per unit time. Flow rates are incredibly important in chemical engineering as it gives us a whole new way of measuring quantities. In chemistry class or in chemistry lab, whenever you carry out a reaction, you have very small amounts of mass, of liquid, of whatnot. You may weigh out 3.0 grams of your solute. You may mix together about 500 milliliters. Those are fairly straightforward and they're just single values. In industry, in the real world, when we're making solutions, when we're dealing with oil and natural gas, when we're making food, We don't want to just be making little bits and amounts at a time. That's really inconvenient. A lot of times when we have solution, we want things to pass through continuously. We want water to go through constantly the whole time. Because of that, flow rates are a really useful value. Flow rates tell us how much of this substance will be passing through our pipe or passing through whatnot per unit time. There are two really important values that come with it. Mass flow rate, represented by an m dot for purposes of this lecture and these lecture series in general. M dot is defined as m over t, where m is the mass and t is time. Volumetric flow rate, v dot, will be volume over time, v over t. It's fairly straightforward when it comes down to it to understand what our flow rate is, but these values are really important. Generally, a time won't even be given with it, but it allows us to understand our process a little bit better. Understanding we're continuously feeding in some compound, we're continuously feeding in benzene and toluene, we're continuously feeding in water. The flow rate allows us to measure that with different types of units. These units, for example, for mass flow rate are kilograms per second. For volumetric flow rate, they could be liters per second. It could be, doesn't necessarily need to be per second. It could be per minute. It could be on a per hour basis. All that matters is that it's some type of unit with respect to a time unit. Density can also be related by the flow rates. In our previous slides, we said density was mass over volume. Density can also be the mass flow rate per the volumetric flow rate. Just another definition, and you may have to use mass flow rate and volumetric flow rate to solve for density instead of using mass and volume. Quick example for flow rate. What is the total mass of water that will accumulate in a vat if the water's mass flow rate is 5 kilograms per second and the water is flowing for a minute? So we can use the definition that we previously established. M dot, or mass flow rate, will be mass divided by time. So you can see here we have the values that we need for this. M dot is going to be 5 kilograms per second, and our time will not be 1 minute, but we will use 60 seconds because kilograms per second is our unit for the mass flow rate, and we want our units to match. Because of this, we can do a simple multiplication, and we get m is equal to 300 kilograms. So we know 300 kilograms of water will accumulate in our vat. Specific values are similar, but the only difference here is that instead of measuring things per unit time, it's going to be per unit of mass. It's going to be on a mass basis. Some of the most common one that you're going to end up seeing with this is going to be specific volume. Specific values are generally represented with a hat on top of the letter. So in this case, V hat. That's going to equal V over M, or volume over mass. It's also going to equal the reciprocal, or the inverse of density. It's going to be 1 over rho, because if you look at it, density is M over V. V over M is just the reciprocal of that. So we know specific volume can be 1 over density. Specific enthalpy, as you remember, enthalpy is the amount of energy that a compound may have, just sometimes the energy that's given by reactions, by breaking those bonds, by forming those bonds, by an increase in temperature. That also do with enthalpy. Specific enthalpy is the enthalpy that a substance has per unit of mass that it contains. And finally, there's also specific work. Work can be amount of energy that you put in a system or amount of energy that comes out of a system. And if it's per unit mass, that means that the amount of mass that we're handling within this system plays a difference in the amount of work that goes in or comes out of it. These are just a few examples of specific values. Almost every quantity can be specific if you take it with respect to mass. These are just a few common ones. And this latter two, we're going to see a bit more as we deal with energy balances, but that top one could show up in some material balances. Quick example. What is the specific volume of a 2.0 liters of a solution if it has a mass of 4.0 kilograms? Well, going back to our definition, we know specific volume is volume over mass. We have a volume, we have a mass. It's going to be 2.0 liters divided by 4.0 kilograms, giving us 0.5 liters per kilogram. If we want to convert it to another unit, something that's a little more common, like SI units, we can convert the liters to meters cubed, giving us 5.0 times 10 to the negative fourth meters cubed per kilogram. It really doesn't matter which one of these you have as your final answer. If a problem does not ask for specific units at the end, it can be whatever units you want. Just usually stick to some common ones: meter cube, liters, kilograms, moles, or whatnot. Now we're going to take a look at stoichiometry and concentration and its various definitions and ways of finding it. So in order to convert between mass and moles, It's fairly straightforward overall. So to convert mass of a compound to the number of moles of a compound, we need to divide the mass we have by the molar mass of that compound. Quite a few times that we say compound in this, so looking at it as kind of an equation, we can take whatever mass that we currently have of our compound. It can be, 18 grams, it could be 20 grams of water or whatnot that we have. We divide that by the molar mass of our compound, that'll be the molar mass of water, and that will equal the number of moles of the compound. This should hopefully be something that you talk about in high school chemistry class. Going the other way around, converting the number of moles of a compound to the mass of a compound, is just rearranging that top equation. Multiply the number of moles by the molar mass of the compound. That's going to go ahead and give you the mass of the compound. Number of moles times molar mass of the compound. Really quick example. How many moles are in 36.03 grams of carbon? Just simple elemental carbon. You can look on a periodic table, look online. You'll find that the molar mass of carbon is going to be 12.01 grams per mole. Now that we have the molar mass, we can go ahead and use this equation. We know that the number of moles of carbon is going to equal the mass of carbon, 36.03, divided by the molar mass of carbon, which is 12.01 grams per mole. Carrying out the division will give us about 3 moles of carbon. Now we're going to take a look at concentration. Concentration is really important, especially when you delve into chemistry, when you delve into analytical chemistry. Understanding concentration, how it plays a role, is really, really important. Really quick, we're just going to go over some definitions that are important to know when talking about concentrations. So we have a solution. A solution is a mixture in which a substance, which is usually solid, is uniformly dispersed within a generally larger amount of liquid. It can be something else other than liquid, but generally you have a small amount of solid and it's dispersed throughout a liquid. And it's uniformly dispersed into small pieces. The solute in a solution is going to be the substance that's uniformly dispersed within that solution. That solid that we talked about, that's going to be the solute. Contrastingly, the solvent is the liquid the solute is going to be dispersed in. You have the solid, which is your solute, you put it in a solvent. And the most common solvent is water. And when we do use water as a solvent, we refer to that solution as an aqueous solution. And then finally, concentration is simply the measurement of the amount of solute within that solution. How much of that solid did I put in that solution in the first place? How does that value vary with respect to the solvent or with the volume of the solution? That's going to be something that we talked about here, and the ways we can measure concentration. There's quite a few different ways we can actually measure a concentration. The most common way you're going to see it represented is by molarity. Molarity is defined as the moles of solute that you have in your solution divided by the total number of liters, or the total volume of your solution, the total volume of the whole solution. That's molarity. Generally, you'll see the units for molarity as moles per liter, or it has to be moles per liter, but more commonly represented by a capital M. Molality is also an important way to measure concentration. That's going to be moles of solute divided by the kilogram of solvent, not kilogram of the whole solution, just kilograms of whatever solvent you're using. Parts per million is defined as the mass of the solute, whatever mass of that solid you're putting in, divided by the total mass of the solution times 10 to the 6th. Parts per billion are going to be mass of the solute divided by total mass of the solution times 10 to the 9th. Those are ways when you only have just a tiny little bit of solute in there. Parts per million and parts per billion are really effective ways of measuring that concentration. Let's go through an example. This is going to be a little bit more of a challenging example here. What would be the molality of 200 milliliters of a 5.0 molar solution of sodium hydroxide? Assume the density of the solution to be 1.24 grams per milliliter. So we have quite a few different values here. We have a volume that we're taking from our solution. We have a molarity of a solution, and we have a density for our solution. So how are we going to find molality? Let's go back to the basic definition. Molality is going to be moles of solute per kilogram of solvent. So we need those two quantities to find the molality of this 200 milliliter solution. To find the moles of solute in the solution, it's going to be our first step here. It's not going to be just looking at that 5.0 moles per liter. It's not just 5.0 because we're only taking 200 milliliters of it. So because of that, we need to kind of rearrange the definition of molarity. Remember, molarity is going to be moles per liter. So if we want the moles of solute, we need to take the molarity of our solution and multiply it by the volume. So we have both of these values here. We know the molarity is 5.0 molar and the volume is 200 milliliter. We can plug these in like this. We're not going to use 200 milliliter for our volume though. We'll use 0.2 liters because we want our units to cancel out. Moles per liter and liters. Those will cancel out the liters and you're going to be left with moles. And when you multiply, you're going to get 1.0 moles of sodium hydroxide. That gives us just the moles of solution. Now we need to go ahead and solve for the mass in kilograms of our solvent. Definition of molality. Find the mass of the water solvent. This mass will be the difference between the mass of the solution and the mass of the solute. You have your whole solution, which a mass we can find, and the mass of the solute, another mass we can find. If we take the difference, that's going to give us the mass of the solvent. So to find the mass of the whole solution, we can use the density. If we take the density, because we're assuming that's the density of the whole solution, we can rearrange the equation a bit to find the mass. So we have our density, 1.24 grams per milliliter. We can multiply it by the volume of our solution, which is 200 milliliters. Doing that will cancel out the milliliters, leaving us with 248 grams of solution. That's total mass. Now we can find the mass of the solute by itself. Remember, the mass of the solute is going to be the number of moles of solute times the molar mass. We found the moles of solute earlier. We said it was 1.0 mole of NaOH. So we can take the number of moles that we have, multiply by the molar mass. In this case, it's going to be 40.00 grams per mole. Remember, you can look in a periodic table, look online. You need to take the molar mass of sodium plus the molar mass of oxygen plus the molar mass of hydrogen. Multiplying that out, you get 40 grams of solute. Like we said, the mass of the solvent is going to be the difference between the mass of solution and mass of the solute. It's represented right here. It was 248 for the whole solution and 40 for just the solute. Taking the difference, you get 208 grams or 0.208 kilograms. Now that we went ahead and solved for the number of moles of solute and the mass of the solvent, we can now use the definition of molality to go ahead and solve for it. Molality is going to be 1.0 moles of NaOH, that's the value we solved at the very beginning, and 0.208 kilograms of H2O, that's that mass that we found. Dividing those two, you're going to get 4.81 moles of NaOH divided by kilograms of H2O, and that will be your molality. Sometimes units of molality are represented by just a lowercase m, but this is a good way to just remember that it's moles of solute per kilogram of solvent. Now that we finished talking about concentration and stoichiometry, let's go ahead and look at mass and mole fractions. So remember, mass and mole fractions, those are really, really important when it comes to chemical engineering. Very rarely do you have just an amount of one substance. A lot of times you have multiple compounds, and a lot of times it's just fractions of compounds that are in a pipe, that are in a stream, that are flowing through, that have a mass flow rate. So a lot of times it's really important to convert between a mass fraction of that amount of volume that you have and the mole fraction of that amount that you have. So to convert from mass fraction to mole fraction, you need to do the following. So step one, select a total mass to use as a basis, generally a power of 10. So if you know that I have a certain solution, I have a certain feed that contains so much water, so much carbon dioxide, so much oxygen, so much nitrogen, and you know that you have 100, that you know you have mass fractions of it, and you want to convert to mole fractions, you select a basis. And it's most easy to select a power of 10, because then that makes the next step really easy, which is multiply the mass fractions by the basis to get the amounts of mass that you have for each compound. So you take your mass fraction, multiply by that basis. That's going to tell you how much your mass is for all those compounds that you have for your water, for your carbon dioxide, for your nitrogen, for your oxygen. Next step then, divide each mass of each compound by its corresponding molar mass for molar amounts. By doing that, by dividing by the mass fraction, as we talked about earlier, converting from mass to moles, you get molar amounts in that case. Then divide each mole amount by the total number of moles that you have. It's going to be every single molar amount added together. It's going to be total number of moles. Divide that, and that's going to give you your mole fractions for each of your compounds. Going the other way around has very similar steps. If you start with mole fractions and you want to convert to mass fractions, you need to do the following. Select the total molar amount as a basis, generally power of 10. Really easy one that I use, select a basis of 100 moles. Step 2, multiply the mole fraction by the basis for molar amounts of each compound. Then, instead of dividing, this time you're going to multiply each every single amount of moles that you have by its corresponding mole fraction, and that's going to give you mass amounts in this case. And then finally, you will divide each mass amount that you get from step 3 by the total mass, and that's going to give you the mass fractions in that case. So those steps that I listed out, they may look a little bit daunting, but it's very methodical. You just go through and you go through each of those steps for every single compound that you have, and that's going to go ahead and give you let you convert from mass to mole fractions. What's really nice about these calculations, though, is that they're really useful to do in a spreadsheet using Google Sheets or Excel. Makes it really, really easy because you're performing the exact same operation on every single compound that you have. You could type everything in your calculator if you want, but it's really nice because using Excel, using Google Sheets makes it really, really easy to go ahead and just solve for these automatically. I'll probably make another video talking about how to use just some basics of Excel, or there's so many different online tutorials that talk about how to use Excel as well, or using Google Sheets. They're very similar. But as you can see here, this is an example of what a spreadsheet could potentially look like. You can see you can select a basis here, putting a number in here. That'll be really important. And then entering the mass fractions that you have. And then letting the spreadsheet do it for you, letting the spreadsheet automatically multiply that 0.15 by 100 and doing it for all the other compounds. And then entering your molar masses and then letting the spreadsheet automatically take the mass divided by the molar mass to give you the mole amounts. And then letting it add the molar, all those mole amounts together and find your mole fractions. A really important thing that a spreadsheet can do too, so you can automatically check your mole fractions and making sure they add up to 1. If all the mole fractions that you have added together don't equal 1, you know you made a mistake somewhere because all the mole fractions added together need to equal 1, similar to the mass fractions. This spreadsheet, this is just something I created really quickly, and I will actually put a link to the spreadsheet that you can copy and use on your own in the description for this video. So go ahead and check that out if you would like to use a spreadsheet like this when calculating between mass and mole fractions, and I have another one for doing vice versa. Now that we finished talking about converting mass to mole fractions and mole fractions to mass fractions, let's talk about just basic calculus, differentiation, integration. Polynomial differentiation should be something that you're very, very familiar with by now if you've taken Calculus 1. Just simply using the power rule and the reverse power rule can be used to take the derivative and antiderivative of polynomial functions. So let's say, for example, and this should be a really quick refresher for you, if you're given a function f of x, it equals some coefficient a times x to the nth. If you want to take the derivative of f, represented as df dx, or f prime x, that's going to go ahead and use the power rule. You'll end up with n times a times x to the n minus 1. And then if you want to take the antiderivative of f with respect to x, it's going to be using the reverse power rule. So you get a over quantity n plus 1 times x to the n plus 1. I'm really only showing how to do polynomial ones here because in mass and energy balances, just being able to do polynomial derivatives and integrals are going to be the most important. Now, another really important thing that's going to be used a lot in especially energy balances are going to be the second fundamental theorem of calculus. And as you remember, the second fundamental theorem of calculus is listed below here. The definite integral from a to b of f of x dx is equal to the antiderivative of f of b minus the antiderivative of f of a. That's going to be very, very useful, especially as we do our energy balances. And it's going to be really nice to know how to do this on your calculator as well. I'll make another video showing how to, on basic graphing calculators, be able to do this automatically. So you do not need to do this by hand. That being said, we'll give a really quick example of how to do one by hand, really, really quick, just to remember what exactly is happening with this integration. So let's say we have the following definite integral. Limits are from 0 to 2. So we can see here, we're going to use our reverse power rule in this case. So we get 1/3 x to the third plus 5/2 x to the second plus x ranging from 0 to 2. Those are going to be our limits here. Then what we do is we make sure to take our f of b, or capital F of b minus capital F of a. So what we do is we plug 2 into that equation for x here. So you get 1/3 2 to the third plus 5/2 2 to the second plus 2. And from that, we will subtract the same thing, but plugging zeros in, which sure enough is going to give us just 0. So we end up with, if you evaluate it, 44 over 3 minus 0, which of course will give us 44 over 3. Knowing how to do this here, how to do these definite integrals is going to be really important, especially as we delve later on in the energy balances. That being said, that is everything I have for the prerequisites here. Remember, if anything that we touched on was not familiar to you or something that you do not exactly remember, please go ahead and check out other resources. Check out your notes on what exactly those topics are covering, because it's really important to be able to do that, especially as we delve later into mass and energy balances. That being said, that's going to be the only video I have on prerequisites, and our next video will actually start with the background for mass and energy balances. So that being said, thank you.